这个项目呢，你就要自多一点。我有点，我是提前看这个。
All right, let's get going. Today we're going to be talking about Hamiltonian, Markov chain Monte Carlo. After we talk about the fact that Hamiltonian Markov chain Monte Carlo was developed largely at Columbia University, and so this applies. This in Columbia's view applies every week, even though what we've talked about so far this semester was all figured out well before I was even born. So, couldn't possibly really have anything to do with that. Moreover, this thing, which Columbia makes me say, makes it sound as if I was the person who came up with Stan or the Hamiltonian Markov chain Monte Carlo algorithm in Stan, which is not true. It was a group effort. I was part of that group. But my contribution to that group was not really to the aspect of Stan that we're going to start talking about today, namely the algorithm to do Markov chain Monte Carlo. That was primarily the idea of Matt Hoffman, who was a postdoc starting in 2010 at Columbia. But in any event, Columbia is not really interested in those distinctions, although you should be. So before we get to that, I want to talk about a few things that we didn't get to last week. One is the idea of a bivariate random variable with a continuous parameter space or sample space. So we're talking about a plane here. We can define the CDF of continuous random variables and evaluate it at x and y given some parameters of theta as the probability a continuous random variable capital X is less than or equal to a given value little x, and simultaneously continuous random variable capital Y less than or equal to a given value little y. We can define that as the bivariate CDF. And if that is the definition of the bivariate CDF, we can take the so-called total derivative of the bivariate CDF to obtain the bivariate PDF by differentiating capital X first with respect to x. So that's the partial derivative, essentially holding y constant. You differentiate that with respect to x, you get a new function. And if you partially differentiate that new function with respect to y, then you get a function little f. It's going to be non-negative because the CDF is increasing function in both dimensions, so the partial derivatives are going to be positive. Moreover, little f will integrate to 1 if you integrate it over both x and y. And so, fundamental theorem of calculus, we can conceive of capital F as being the integral of little f up to little x and little y. It's really just the reverse of this. And if we wanted to have a PDF for x alone, irrespective of y, we could take the joint PDF of x and y and integrate it over the entire sample space of y. Or conversely, we could do it, integrate it over the sample space of x alone. We would get a function, a PDF for y in isolation. So we get those. And if you can get the marginal PDF for x or y, you can take the joint PDF divided by the marginal PDF, get a conditional PDF, either given x or given y. So here I've stated this with x and y as random variables conditional on theta. But as you hopefully have dawned on you by now, even though I may not have said it, which I should have, is that Bayesians treat probability manipulations in exactly the same way, whether we're talking about an observable x or a parameter theta. So we could, multiply all this by a prior PDF for theta, and the mechanics of it are the same. And the mechanics of it are the same if we're taking the modern-ish view where we draw theta from some prior distribution, and then we draw x and y from some other distribution conditional on the realization of theta. We're doing the steps in exactly the same way, irrespective of whether we're talking about something that is potentially observable, like y, versus something that is not observable and it's just a creature of our model, like theta. And that's where the frequentist approach, or that's where Fisher's frequentist criticism of the Bayesian approach happens. He thought you shouldn't be able, or you should not use probability in exactly the same way, whether we're talking about an observable outcome or an unobservable parameter, because observable outcomes can, in principle, be randomized, like in a randomized control trial, whereas theta, there's no experiment we can do to randomize theta, even though it kind of makes it look like it when we do simulations. All right? So okay, a couple more things. So suppose we have a, this could have been omega, but it's two-dimensional, and we have some function g that depends on both x and y. So let's say the output of g is going to be another random variable called z. So in general, the expectation of the g function, which is to say the expectation of z, would be constructed by evaluating the g function, all possible values of x and y, weighting them by the bivariate PDF of x and y given whatever parameters theta, and integrating that over both dimensions, all possible values of x, all possible values of y. So that is the general formula for the expectation of a bivariate function. This sort of presumes that these integrals converge and are well defined, and if not, then we say the expectation of g doesn't exist, or maybe it's infinite, something like that. But usually if we're doing this, it's going to converge, and so we have a well-defined expectation of g. And in particular, if g is the function x minus its expectation multiplied by the quantity y minus its expectation, then this integral yields an expectation of g that is special enough. It has its own name, namely the covariance between x and y. So if g is defined this way, the expectation of g is the covariance between x and y. So as we can see, if x tends to be above its expectation when y tends to be above its expectation, then when we do the weighting of it, we're going to tend to get a positive covariance. Conversely, if x is below its expectation when y tends to be above its expectation, then it's more plausible that we get a negative covariance, and it can be shown, although I don't show it here, that the expectation of g is equal to the expectation of the product of x and y minus the product of the expectations. Moreover, if x and y were the same variable, then we would have the formula that we've talked about previously for the variance. But in general, if we're doing it this way, we're doing it where x and y are distinct concepts, in which case this is the covariance between them. Variance can only be positive, but covariance can be negative, and it's often denoted by the symbol sigma with like subscripts for what it's the covariance of. If we slightly change the g function, to divide by the standard deviation of x and the standard deviation of y. When we multiply these two things together, then if we do the integral to get the expectation of g, these things in the denominator here are constants, so they can come out front of the integral sign. And now what we're left with is the integral, double integral, defining covariance. So that leads us with the conclusion that the expectation of this g function is the covariance between x and y divided by the standard deviation of x divided by the standard deviation of y. And that expectation is even more special and has its own lowercase Greek letter rho because this is the correlation between x and y. Correlations must be between -1 and 1, and correlations don't have units. And that's because sigma xy is in the units of the product of x and y, which is kind of a weird thing to think about. Like the covariance between age and income would be in units of like dollar years, which is weird. But when you divide by the standard deviation of x and the standard deviation of y, those are in their respective units. And so all the units cancel. And so correlation is a measure of linear association between two continuous or even discrete random variables. Is going to be between -1 and 1, and it does not depend on the units in which the variables are measured.
Yes. So I was going to ask, what exactly is the difference with covariance and correlation? Because I feel like they kind of do the same thing. So
they are both measures of linear association between two random variables. Neither of them captures nonlinear association. But to answer your question most directly, covariance divided by the respective standard deviations is correlation. And so covariance is tied up in the units in which x and y are measured. Correlation cancels the units. And for that reason is essentially preferable. So it wouldn't matter if you measured your income in dollars or euros or bitcoins or whatever. The correlation would remain the same with age. Okay, question?
So the concept of covariance and correlations on this slide are slightly different from the concept that we learned about the covariance correlation from the introduction level statistic class. Because this is in the framework of the Bayesian style, they given you are prior to believe you get the covariance and correlation, right?
Yes. So this, I wrote it just conditional on theta, which is how frequentist would, anticipate it being used. But yes, if you had a prior on theta, the correlation between x and y would depend on that prior. So it would be a function, like let's say you had some prior on theta, it would be a function of that prior rather than just a single scalar number. And that is a bit different. Moreover, what you presumably learned, hopefully learned, in your more introductory class is an estimator of correlation, particularly a point estimator of correlation. What happens if you go into R and say core xy and you get out a number? That is the estimated correlation. But one of the difficulties with introductory classes is that people learn how to estimate stuff, but they don't learn what it is they are estimating. So what it is they are estimating when they call the core function in R is the expectation of this g function. So this is how correlation, the concept, is defined, or how it's defined in an infinite population, if you like that abstraction, with like an infinite number of people or something like that. And maybe in a survey you observe a finite number of people and you want to estimate the population correlation from a finite number, and as point estimators go, the one that's programmed into R is not horrible. But from a Bayesian perspective, we're not super enamored with point estimators. We want to estimate stuff with random variables, particularly posterior distribution conditional on the data that we know and the priors that we have. And so we get, a PDF estimator of an unknown correlation rather than a point estimator. Now, if we have a posterior distribution, a function, we could squeeze a point estimator out of that with the mode, which is not very good, or the mean, which is better, or the median, it's also, perfectly good. So if you have a whole function, we could get 1 point if that was absolutely required. Moreover, if we have a whole function, we could slice out an interval of it. So if you have a whole function, you can get point or interval estimators out of it. But if you start with a point, like maximum likelihood does, or any frequentist thing does, you can't go from a point to a function. You can't really go from a point to an interval, because the interval requires 2 points. So you can go from the more general thing to the more specific thing if you want. But if you start with just a point estimate, there's nowhere to go. And thus it's a much less rich answer. Thus, you can't really answer the questions that you want to answer with a limited point estimator. So the way in which, or one way in which this comes up is the so-called bivariate normal distribution with 2 continuous random variables. And it has this PDF, which depends on 5 parameters that ordinarily we might want to estimate. Those 5 parameters are the expectation of x, the expectation of y, the standard deviation of x, the standard deviation of y, and the correlation between x and y. And the bivariate normal PDF has this expression here, which looks rather daunting, but it can be rearranged into this expression on this line here, where if we just look at over here well, that's just the marginal PDF for x. Does not involve any y over here in black. So from this over, just a marginal PDF of x. And then it gets multiplied by this more colorful expression here, which, if you sort of squint at it, also takes the form of a normal PDF. But it involves both x and y. Up here, we got x, over here, we have y. And so the more colorful expression to the right is a conditional normal PDF for y given that capital X is equal to little x. And that conditional normal PDF for y has new parameters. Expectation equal to the marginal expectation of y plus the ratio of the standard deviations multiplied by the correlation multiplied by the difference between x and its marginal expectation. So that, this mu here in red, conditional expectation for y given x. Also in blue, we have conditional standard deviation for y given x equal to marginal standard deviation of y multiplied by the square root of 1 minus rho squared, but because rho is between -1 and 1, the square root business is going to be less than 1. Consequently, the conditional standard deviation of y given x is going to be less than or equal to the marginal standard deviation of y, but it's only equal to the marginal standard deviation of y if rho is exactly 0, which is to say x and y are uncorrelated. with each other, and in the case of normal distributions only, or not only, but in the case of normal distributions and very few other cases, the absence of correlation implies independence. So if rho is exactly 0, x and y are not only uncorrelated, they are independent of each other, in which case no surprise that the conditional standard deviation of y given x would be equal to the marginal standard deviation of y if there is in fact no association at all between x and y. Knowing the value of x if rho is 0 doesn't give you any information about y. But in the more general case where rho is not exactly 0, then knowing the value of little x gives you some information, depending on the magnitude of rho, information about y, and consequently the conditional standard deviation of y is less than the marginal standard deviation of y irrespective of x. So we started off with bowling in the discrete case because bowling had the simplest conditioning mechanism that I could come up with, namely the probabilities for the number of pins you knock down in the second roll of a frame of bowling are 10 minus x1. x1 is the number of pins you knock down on the first roll of that frame of bowling. In the case of continuous random variables, bivariate normal is the simplest conditioning mechanism I can come up with, even though it's considerably less simple than bowling. But it is still simple in the sense that it is linear. This is a linear function of x. And also, the blue thing here actually doesn't depend on the value of x. It just depends on the value of rho for the correlation between x and y. So bivariate normal, it's the simplest bivariate distribution with dependence, where we can fairly easily understand how conditioning on x changes the conditional expectation of y given x and the conditional standard deviation of y given x. Also, this bivariate normal stuff generalizes fairly straightforwardly to multivariate normal, where we're not just considering two, but many variables. So how are we feeling about the bivariate normal distribution and our ability to factor the PDF into a marginal normal for x irrespective of y and conditional normal for y given x? We can also do it the other way around. Marginal for y, conditional for x given y.
Can you have a discrete and a continuous variable at the same time with like part of
Yes,
this?
that would not be normal.
Okay.
It would also not be common, but it does happen. Indeed, it did happen when we considered bowling with continuous ability, and we considered the trivariate distribution of ability, number of pins knocked down on the first roll, number of pins knocked down on the second roll. That was an example of what you might think of as mixed.
Okay.
Continuous and discrete, but if any of the variables in a joint distribution are continuous, then you're basically in continuous. You're going to have to do some integrals.
Okay.
So you're in kind of the continuous world.
Okay.
But once you do the first integral, then it's discrete on the pins. Questions? All right. So how would we draw from a bivariate normal? It'd be like this. We draw a marginal normal distribution for x given mu x and sigma x, presuming that those are defined, they're given, or else we've already drawn them from their prior in the more Bayesian way. And then y given x, given the realization of x, we would make the mean be this expression here, except not this expression here. This expression here should have a row in it, so that it is the thing in red on the previous slide, and then the SD got chopped off, but it's the marginal standard deviation of y times the square root of 1 minus rho squared. So that's just how we would draw from bivariate normal given the parameters. All right, so basically just how would we draw from the distribution defined on this slide here. Okay, so we got that. And if we do that, it looks like one of these things, which fortunately is working. So this is x over here on this axis, y over here on this axis, and the joint density f on the vertical. And so you can rotate this thing around. Once you render it, you can, rotate it around so you can see things a bit better. So if you look straight down on it, the ones in brighter or darker colors here are having more density. You can see it's got a little bit of a tilt to it. That's due to it having a non-zero correlation. But if we rotate it around and look directly perpendicular to one of the axes, we see a normal PDF shape for the X margin. And if we turn it around sideways, look exactly perpendicular to the other axis, then we see a marginal normal looking PDF for Y irrespective of X, because when we look at it this way, we can't see what's behind, which is what comprises the joint. But if you look at it, something like this, then you can see it's actually an illusion of 3 dimensions. So it looks like that. Okay, so that's into the normal. Back to the Pfizer-BioNTech COVID vaccine. So this we did before. This is what if we put a normal prior with an expectation of 0.3 and a standard deviation of 0.15 on the vaccine effectiveness. So we draw that, truncated to be less than 1. Map vaccine effectiveness to theta using that formula there, and use theta when we draw y from a binomial with size 94, 94 being the number of people in the randomized controlled trial who got COVID, theta being the probability of you being vaccinated given that you have COVID. As it turned out in the trial, there were 8 people out of 94 who got COVID and were vaccinated. The other 86 were unvaccinated. And so if we condition on the data, that means filter according to whether the simulated value of y matches the observed value of y in the observed data. Now we are conditioning on the data to get updated beliefs about the vaccine effectiveness. But when we do this, so we did that before, but what I didn't harp on at the time is when we filter for y being exactly 8, we're only left with 239 draws-ish. That's random, but ballpark. But we started with 10 million and ended up with 239. Consequently, our modern-ish estimate for the marginal probability of y irrespective of theta is 239 over 10 million, a very small number. We could do that deterministically by constructing a joint function, joint distribution PDF for the numerator of Bayes' rule. Take the normal PDF as our prior on the vaccine effectiveness with expectation 0.3 and standard deviation 0.15. Multiply it by the binomial PMF for 8 observed people who got COVID and were vaccinated out of 94 people who got COVID, and the probability being theta, just that function there. If we then integrate that numerator of Bayes' rule from negative infinity to 1, we get a number 2.38 times 10 to the negative 05. which is also very small. It's like different in the third decimal place from our simulation. So either way of doing this would be fine. But it's kind of just barely fine. It is fine, but barely fine. Barely fine because, we can see here we get an estimate of the error in the integral. And this estimate of the error is only 1 order of magnitude less than the thing that we are estimating. So we might not be super confident that this integral is estimated accurately enough, which is kind of another way of saying, even if we do 10 million, start with 10 million draws, if the probability of the data is so small that we're only left with 239 after we filter, this could have randomly been like 225, 250, something like that, bounced around a little bit. And so in relative terms, we're not super certain about it. But anyway, it's definitely fine. It was fine when we did it. It would have been fine if Pfizer did it. But it's pretty clear that most of our original 10 million draws were totally wasted. Not a big deal. Only takes like 2 seconds to do. Doesn't really matter how many we waste. But it does not seem like it's a particularly efficient way to proceed by drawing from the joint distribution and then filtering according to whether it matches the data. Moreover, this was just with one discrete observation. We would have lost even more if we'd had more than one observation, which we ordinarily do. And we would have lost all of them if the observation that we had was continuous. So this idea of drawing from the joint and then filtering is a great way to learn the idea behind Bayes' rule, conditioning on the data, getting updated beliefs about the parameters. But it's really only feasibly practical in the case of like binomial data and one observation. Well, it's the sum of 94 Bernoullis, but it sums to one observation. Otherwise, you're just going to end up throwing away way too much. And so I've been describing this as modern, but this is not exactly what the 1990 paper did. Like, this could have been done in the 1980s. What the paper that I talked about the first day came out in 1990, Journal of the American Statistical Association, did was propose a scheme where we can draw from the conditional distribution of the parameters given the data and the priors directly. So just draw from that conditional distribution rather than drawing from the joint and filtering and throwing away most of your draws. Is there a way that we could draw from this conditional distribution directly and not throw away anything? Or maybe not throw away very much. Not throwing away something that depends on the probability of the data, which is always going to be pretty small. But something where we can maybe like control what proportion we keep. And that's what really changed everything in terms of going from ancient to modern with these ways of directly drawing from a conditional distribution through Markov chain Monte Carlo, which we're going to talk about for the rest of today. So what I've been calling modern, you could maybe more think of it as like medieval. Things didn't really get modern until MCMC. So just a bit more on this. So Pfizer didn't actually do this. I did this. And so that gets to this idea of principles that you might choose priors with. First principle, do not use so-called improper priors. Priors whose PDF does not integrate to one. Historically speaking, such improper priors were remarkably popular because people mistakenly thought that they were not subjective, when really they were just as subjective and they were improper in the sense that they don't, the PDFs don't integrate to one. Moreover, if you don't have a well-defined random variable whose PDF integrates to one, how would you draw from it? You can't. And so that's simulating parameters and data is a big aspect of what we're doing in this class, and you can't do that if you don't have a well-defined prior distribution to begin with. So historically, you will see people use improper priors, and in a manner of speaking, sometimes, not always, you can get a proper posterior distribution even if you start with the improper prior. But that's not guaranteed, and you really don't want to have to check as to whether that's going to hold in a particular case. What is guaranteed is if you start with a proper prior distribution, the posterior distribution is guaranteed to be proper. Both the prior and the posterior will have PDFs that integrate to one, and so you don't need to check anything. It's already been guaranteed for you. So that's why favor in this class using proper priors only. But there's lots of proper priors. How might you choose among proper priors? So, like I said, there was kind of mistaken impression that those were less subjective than other priors, which is not really true. So if we're choosing priors subjectively, a common way of doing things is to try to make these priors be only weakly informative about the parameters to give more room for the data that you've collected to be informative about the parameters. And I think that is what Pfizer was going for, except Pfizer got off on the wrong foot by restricting itself to a prior for which it could do ancient calculations, namely the beta prior over theta. But theta is kind of a weird thing to begin with. But they said, okay, if we have to use a beta prior, we're choosing to only use the beta prior, so we can do ancient calculations utilizing conjugacy with the binomial likelihood, and the posterior will be in the same beta family with parameters A star and B star. We did that. So Pfizer got itself on the wrong foot by insisting on only doing ancient calculations. And then, okay, if I have to use a beta prior, they sort of chose A to be about 0.7, and they chose B to be about, or exactly 1, in order to give themselves a posterior, or not posterior, like a prior mean or prior median around 0.3. Which is kind of the threshold that the FDA usually uses for approval. So as good a chance to be less than 0.3 as it is to be greater than 0.3. And the vaccine effectiveness. But what we saw was if you insist on using a beta prior and you use like the FDA guidelines to give a prior median of about 0.3, what you get is a whole bunch of probability of negative vaccine effectiveness, which no serious person believed, and a whole bunch of probability on the vaccine effectiveness being very close to 1, which no one seriously believed as of 2019, because the mRNA vaccines had never worked through 2019. So by a combination of things, Pfizer ended up with what I would regard as a pretty bad prior. It didn't correspond to something that anyone believed. But it was in the weakly informative vein. And thus, when you got overwhelmingly informative data, of the 94 people who got COVID in the trial, only 8 of whom were vaccinated, allowed a massive updating of the vaccine effectiveness to where it was a no-brainer for the FDA to approve it. So wasn't a great choice of prior, but the data was so overwhelming that it kind of made their not great choice of prior moot. Would have been better, I think, to do this with the normal prior centered about 0.3 on the vaccine effectiveness, standard deviation about half the mean. So we're just putting a little bit of probability that it's less than 0 negative vaccine effectiveness. But, you know, to get approval, it would have to get shifted right a good bit. Did you have a question? So anyway, I think what I did on the previous slide is a better version of what Pfizer should have done, but both going for 2. Entropy maximization was talked about in the Lancaster reading, will be talked about a lot more in the McElreath book as we go forward. Actually, the normal is the prior that maximizes entropy. So what does entropy mean? It's sort of another way of describing uncertainty. So what maximizes entropy is says, okay, what gives it the most uncertainty, conditional on what we know. And it can be shown that if your parameter space is the entire real line, the distribution that maximizes entropy for a given variance is the normal distribution. Now, we didn't quite have that in the case of this because vaccine effectiveness is not over the entire real line. It's the real line up to 1. But if you put the prior, you know, mean 0.3 and standard deviation 0.5, there's very little chance of getting something greater than 1. So it's in practical purposes, the entire, you know, real line. So the normal would be kind of applicable, and you could make an argument from entropy maximization in favor of using. Yeah.
I usually think entropy is like noise, so in this case, it wouldn't really be noise, right? Like uncertainty.
I wouldn't really say it noise.
Okay.
But so noise is usually contrasted with signal. Signal being information. So this idea of entropy maximization is kind of geared toward letting as much signal come from the data as possible, given what you know, or given what the FDA tells you, which is we're not approving your thing unless it's greater than 0.3 effectiveness, you know, something like that. So anyway, arguments can be made for that. Invariance to reparameterization is another argument that could be made. So this is not invariant to reparameterization. What I've done here is make vaccine effectiveness primitive and then induce a distribution on theta, which goes into the success probability of the binomial. That's the opposite of how Pfizer did it, starting with the beta prior on theta and then making vaccine effectiveness be derived from that. So these prior choices don't entail invariance to reparameterization. And then there's a strain that's a little bit different from one for like objective priors. But objective priors are actually also subjective, so we're not really going to dwell on them too much. So anyway, kind of to summarize these, choose a prior whose PDF integrates to 1 over the entire parameter space. And then if that's normal or that's gamma, whatever, choose the parameters that go into that prior to be consistent with your beliefs or the beliefs of your audience or the beliefs of the regulators who are going to be approving or disapproving of your vaccine for distribution in their country. And if you do it that way, then it's fairly straightforward to conceive of the value added of a study as to how much it moves the beliefs about the parameters from prior to posterior, in the case of the Pfizer study, it moved them a lot, so much so that it didn't even really matter what the prior was. And the important part of the prior is really what values it discounts, not what value is like the mode or something like that. So in this context, it's important to discount the possibility that the vaccine could have negative effectiveness. Once you do that, you're pretty much okay. Another thing that we'll be talking more about in subsequent weeks is that if you're concerned, which you should be, as to whether your prior beliefs about the parameters are unreasonable, you can simulate from the prior distribution, use the realizations of those values to simulate from the data distribution, otherwise known as the prior predictive distribution of the outcome, and see whether the prior predictive distribution of the outcome looks reasonable. If so, then your prior beliefs about the parameters were probably also more than reasonable enough. But a lot of people find the prior predictive distribution easier to work with because it's predictions of an observable. And so you might have some ability to anticipate what the outcome data will look like. And so that allows you to think about these things in more concrete terms, maybe, than just like theta. Particularly like in the case of the Pfizer thing where theta is a weirdly defined quantity to begin with. Whereas you could maybe even ask a doctor who works in a hospital or something, doesn't really know much about statistics. Oh, okay, of like 100 people who come into the hospital with COVID, how many would you anticipate are vaccinated? And how many would you anticipate are unvaccinated? That's the type of question that you might be able to find a doctor who could give you a plausible answer to. And then you'd be, okay, that's what I need to shoot for with my choice of priors on whatever the parameters are. Okay, so we'll talk a lot more about choosing of priors because we're going to have to do it every time, starting this week, next week, all the weeks. But one more thing that we need to talk about before we get into MCMC is this likelihood function, which has come up a couple times on ed discussion, which is not surprising because it's rather confusing terminology because the likelihood function is the same expression as a PDF or a PMF. So if it's the same expression, why do we need two different words for it? Well, we need two different words because whichever way you look at it kind of embodies three distinctions, which are rather important. So first, if we think of this expression as a PDF or a PMF for x given theta, then in mathematical terms, we're thinking of x as the random variable and the parameter theta as being given. Conversely, in the case of a likelihood function, which is the same expression, but we're considering that to be a function of the parameters and the data to be given. So remember, a function is a rule that uniquely maps from some input set to some output set. So implicit in the definition of a function, you have to say what input set you're mapping from, what output set you're mapping to. And so if we're thinking about mapping from the sample space of x, that's actually a different function, even if it's the same expression, than if we were mapping from the parameter space of theta. And that's true regardless of what x and theta are, but it's particularly true if x is discrete. And so the probability mass function maps from a discrete sample space, whereas the likelihood function of the parameters is mapping from a continuous parameter space. So these are obviously different input sets. Consequently, there are different functions. even if the function definition involves the same expression. And as a consequence, if we're thinking this as a PDF for x given theta, if we integrate it over the entire sample space of x, it must integrate to 1 to be a valid, proper probability density function. Or we sum it in the case of a probability mass function, sums to 1. Whereas if we integrate the likelihood function, and the parameters can be a vector of like k values, so we integrate that over the parameter space, well, it will be a positive number if those integrals converge, which they may not guaranteed to. But if they do converge, rarely will they converge to 1. And that's okay, because the likelihood function is not a probability density function, not required to integrate to 1. So that's the main distinction. That's why Fisher actually introduced the word likelihood to distinguish from the cosmetically identical probability density functions when doing maximum likelihood estimation. But when doing maximum likelihood estimation, we often think of the likelihood function not for like given one observation, but given all n observations. But if those n observations are conditionally independent, given the parameters, then the probability of them or the probability density of them, it can just be written as a product from the first to the last observation, all involving the same theta. But third distinction, when we say likelihood function, we often really don't mean the likelihood function. What we mean is the natural logarithm of the likelihood function, which is usually referred to as the log likelihood function. But honestly, people are pretty sloppy about whether they're talking about log likelihood function or whether they say log likelihood function or likelihood function. They're usually talking about the log likelihood function either way, because the log likelihood function is much more amenable to computation. And so if we have a product, this sort of characterizing fact about logarithms is they turn products of positive numbers into sums of logarithms. So if we take the logarithm here, the product becomes a sum, and we're summing the capital N contributions to the log likelihood function. Mathematically, that makes some stuff easier, definitely makes stuff easier on a computer. And so almost never are we working when we're doing stuff on a computer as opposed to when we're doing stuff with a pen. If it's on a computer, we're basically always talking about the logarithm thereof. Now, so with all those distinctions flying around, may be cause for concern, but Bayesians do, and they certainly can, don't have to, use the same log likelihood functions that frequentists do. As we'll start to see next week, one way of building up a Bayesian model is, taking some frequentist estimator like maximum likelihood, combining that with a prior. Instead of using maximization, use MCMC, and all of a sudden you have a Bayesian estimator, which is much better. It yields draws from the posterior distribution instead of just a single point estimate number. It enables you to answer the questions that naturally come into your mind, as opposed to doing some exactly backwards thing that you have to do frequentist with just your 1 point estimate or a function zero. So anyway, Bayesians can use the same log likelihood functions. They oftentimes do. They are not required to. And the Bayesian MCMC estimation actually opens up the possibility that we could use some log likelihood functions that frequentists can't do in practice, because it's too hard for them to find the maximum of a complicated log likelihood function. Whereas that's actually easier for Bayesians to handle, because we don't have to do maximization. So if maximization is like too hard in a particular case for frequentist estimation, it is often the case that just by avoiding the maximization, you can go forward. But anyway, so let's talk about some one more thing that we'll talk about. So just to kind of belabor the point about PDF versus likelihood, say we have this expression here. E raised to the power negative 1/2 x minus mu over sigma quantity squared, and then divide by sigma square root of pi alpha. So for a given mu and a given sigma that's positive, this is a PDF, a probability density function of x over the entire real line, and it integrates to 1, which we can confirm by integrating the d-norm function over the entire real line with given values for mean and standard deviation. Actually, it doesn't matter what values of mean and standard deviation we use. We will get an integral of 1 with maybe tiny amount of error because this is done with little trapezoids rather than symbolically. But anyway, this is 1. What if we take this same expression for a given x and a given mu and try to integrate it over all positive values of sigma? Then this is a likelihood function, and the integral diverges. So it most certainly does not converge to 1. Now, because it's doing this with little trapezoids rather than symbolically, it just says like failed with error message, extremely bad integrand behavior. But that's R's way of saying like, I don't think this is converging. But anyway, it would if we multiplied this by a proper prior over sigma. And instead of integrating just the likelihood, we integrate the product of the likelihood and the prior, then it would converge, at least theoretically. But on its own, it often does not. Which is not a big deal from a frequentist perspective. They're just choosing the value of sigma that maximizes this thing. So whether the whole curve integrates to anything at all, it doesn't matter. They're just finding where the curve is tallest, and then that's their estimate of sigma. But for Bayesians, it does, and so if you get extremely bad integrand behavior, then you probably don't have a proper random variable distribution. Okay, now to Markov processes. What is a Markov process? A Markov process is a sequence of random variables where the future is conditionally independent of the past given the present. Tomorrow, conditionally independent of yesterday, given today. But for the whole sequence, nothing is marginally independent of anything. Irrespective of today, yesterday and tomorrow are not independent. Conditional on today, yesterday and tomorrow are independent. But if you marginalize over all the things that today could be, then you induce the dependence between yesterday and tomorrow. And an example of a discrete time Markov process, let's say we have a random variable capital X, and it has a sequence of values indexed by little t, and it has a conditional PDF of the current value of t given the previous value of t, some PDF, conditional PDF, then the joint PDF of all capital T elements in this sequence given x at time 0, so like Big Bang or whenever that was, is going to be the product from little t is 1 up to t of all these conditional PDFs. So in a Markov process, I only have to condition on the value in the time period immediately previous. So if like t means today, I only have to condition on yesterday. Because conditional on yesterday, it's conditionally independent of last week, or last year, or any time in the past or any time in the future. So conditioning just on the period before is sufficient. I don't have to go back farther in time with my conditioning. This is what makes it a Markov process. And so that, you might say, is a massive simplification. I only have to condition on yesterday. But Markov process is kind of the simplest thing where you can get some really wild behavior just by conditioning on past time.
So this is basically how like prediction works, right? Like basically
Yeah.
if you want to do like predictive analytics.
Right, so if you have a Markov process, you have a relatively simple way of predicting it. I just need to know what it was yesterday. I can predict it today. I don't need to know what it was. If I know what it was yesterday, I don't need to know, or I don't care about what it was last week, last year. That's not going to help me. All the information that would help me predict what it is today is encapsulated by what it was yesterday. And what it was yesterday is sufficient for all the past. So if this is a joint PDF of all capital T realizations, conditional on the realization before the first realization, X naught, then conceptually speaking, we can think of a marginalized probability density function marginalizing over x1 and x2, but leaving x sub t. So leaving a conditional PDF for the last period, capital T, given x naught, the realization before the first realization, marginalizing over everything that happened in between, everything that could have happened in between. So that integral may be very hard to do, but at least conceptually we can think about what it means to cross out all the intermediate realizations and just leave a PDF for the last one given x naught. And the good thing about a Markov process, okay, so we said marginally nothing is independent of anything else. However, as capital T gets large, the conditional PDF of x sub t given x sub naught approaches a marginal PDF for x sub t, so that we can use this sequence for large T to essentially draw from the marginal distribution of the last value of the sequence. If T is large, then unsurprisingly the influence of x sub 0 diminishes to negligible as T gets large. So this drawing T times from this conditional distribution gives us essentially a way to draw from the marginal distribution of the last element of the sequence. And that's what I mean by saying this is a relatively simple idea that can induce extraordinarily complicated probability density function for the last element of the sequence that we can draw from relatively easily, even if we can't do these integrals that would marginalize over all the intermediate realizations of the sequence between x0 and x sub t. So let's be a little bit more concrete about it. A first order autoregressive process is a discrete time Markov process. It is the simplest continuous Markov process because it's linear. This says x sub t is equal to m times 1 minus p plus p times the value of x in the previous period plus an error term that's distributed normal with expectation 0 and standard deviation s. So this is a linear Markov process because the dependence on x in the previous period is simply multiplied by a coefficient p. And because this is the simplest one, we actually can do all these integrals deterministically and prove that as t gets big, the last realization of this process, autoregressive process of order 1, is going to be distributed normal with expectation m and standard deviation s divided by the square root of 1 minus p squared. And we can confirm more or less this statement, which can be proven by evaluating this code, which is a little bit hard to read, so I don't want to dwell on it. But the punchline of it is we're simulating this process, and both the expectation and the standard deviation after 1,000 periods come out to be essentially the same thing as what I asserted could be proven that they would come out to if t were actually infinite as opposed to merely 1,000. All right. So I point this out because, one, this autoregressive process of order 1 is something you might have seen before in other classes. It's pretty basic time series deal. But also it's simple and it's linear. We can prove stuff about it. And then we can do simulations that are consistent with what other people have proven. Okay, so if we visualize an AR1 process, or 10 realizations of an AR1 process with 1,000 time periods, it looks like this. As you might have seen, when you initialize one of these AR1 processes, you have to choose something for x sub 0. I chose it to be a random draw from a Poisson distribution with a mean of 10. It could be anything. It's allowed to be anything. It doesn't even have to be random. At best or at worst, it only affects the rate at which this goes to what we know as t goes to infinity. It does not affect the fact that as t goes to infinity, this is going to converge. So you see these realizations of the 0 period can be pretty big. But it rather quickly settles down. It's kind of jaggedy, but these are 10 realizations of an AR1 sequence. When P is set to 0.5 in this case. So moderate amount of dependence between this period and last period. Question?
So in the last equation, is it that the error is constant throughout each prediction?
Yes, the error
Okay.
is going to be independent of each other, and as mean 0, and standard deviation s, which is a constant for every period. So that is a simplification. But anyway, so the errors are independent of each other. The x's are not independent of each other because it depends explicitly on the previous x, unless p is 0, which it's not. Right. So another way you can think of this, okay, these errors are independent, and we're adding them into the mix as we go along. But the mixing depends on the previous period, so it's random, but it depends on other things besides epsilon. Okay, looks a little bit like that. Which brings us to the concept of effective sample size, which was brought up in the context of the reading on MCMC, even though so far today we haven't even talked about MCMC yet. But we can use this idea of an AR1 process to help us get a handle on the idea of effective sample size. So if we only executed the AR1 process once rather than 10 times, but we kept the last R realizations. So this is 10 independent realizations. I'm going to have to restart this. And I lost it. Okay. So while that's going, or were there any questions about Markov process, AR1, which is a specific, simple but illustrative example of a discrete time Markov process? Anything along those lines? Priors? How to choose priors? This is going to take another 20 seconds, so if you have any questions, spit them out. Otherwise, you can just check if you got a text or something. Here we go. Okay, no more texting. First order, okay, so visualize looks like that. So this is 10 independent realizations of a 1,000 period AR1 process. So instead, what if we only did the AR1 process once, but kept not just the last realization, but the last R realizations? Well, it is nevertheless true that as t goes to infinity, those last R realizations are marginally going to be distributed normal with the expectation m and standard deviation s divided by the square root of 1 minus rho squared. But they're not going to be independent of each other, which affects how we do the estimation using those R realizations. So most of what you probably learned previously presumed that we had like R independent things and we were going to form estimates based on those. Can still form estimates, but have to always keep in mind that the last R realizations of a Markov process not independent of each other, even though marginally speaking they have the same distribution. So they are not IID. They are not independently and identically distributed. They're only identically distributed. They are not identical. They have different realizations because they're random variables. But they have the same distribution, but they're not independent of each other. And it can be shown that in an AR1 process, the correlation between x sub t and x sub t plus or minus n is p raised to the power n. And since p is going to be less than or equal to 1 in absolute value, you can, let's say just strictly less than 1, you can see that the dependence between two values that are separated by n periods is going to rather rapidly diminish towards 0. So they never become completely independent, but the dependence between them becomes negligible the farther the gap is. But it's also going to depend on what p is. If p is close to 0, then they get negligible dependence almost right away. If p is really close to 1, then you need a large gap between them to make the dependence negligible. So those are specifically for AR1 process. In general, for a Markov process, maybe not AR1, could be something more complicated than AR1. If it mixes fast enough, and for the so-called Markov chain Monte Carlo central limit theorem to hold, and we're not really today going to get into the conditions that would ensure that, then we can define the effective sample size in effective as R, the number of realizations of the process we keep, divided by 1 plus double the infinite sum of the correlation between two realizations that are separated by n periods. And so that is going to have to diminish towards 0 in order for this infinite sum to converge. If so, then we can define the Markov chain Monte Carlo standard error estimator for the mean from those R draws to be sigma divided by the square root of the effective sample size, which differs from what you might have seen in previous classes that got into the frequentist central limit theorem, where the standard error of a mean was sigma divided by the square root of n, according to the central limit theorem. we're, in this case, dividing by the square root of the effective sample size rather than the square root of the nominal sample size. What you learned previously about central limit theorems presumed that the random draws that you obtained, samples, whatever, were independent of each other. We need a modification of that in the case of a Markov process where our consecutive realizations are not independent of each other. And typically, the effective sample size is going to be less than the nominal sample size because typically we're dividing by a number that is greater than 1 in the effective sample size calculation. And that was particularly true of what we might call first generation Markov chain Monte Carlo algorithms that started essentially with that paper in the Journal of American Statistical Association that was published in 1990, even though those algorithms had actually been developed before, but the paper in the Journal of American Statistical Association was the first to like tie everything together in terms of being able to use this for statistics. So these first generation MCMC algorithms, specifically speaking, Gibbs samplers, Metropolis Hastings samplers, slice samplers, other things that you may or may not have heard of, they were valid as something goes to infinity, but they would tend to have correlation between realizations that were separated by n periods in between them. It would be close to 1. And so this infinite sum would converge very slowly. And the denominator of the effective sample size would be a pretty big number. And consequently, the effective sample size might be much, much, much less than the nominal sample size R, because consecutive realizations had so much dependence between them. And thus, you'll see, if you read the literature from the 1990s, people saying, oh, I did this for 1 million, or I did this for 10 million. Because they needed 1 million iterations, which back in 1990 would have taken like a month to obtain. It only takes you a second, but this is a long time ago. They needed 1 million nominal to have like 10 effective, because the 1 million that they had were so much dependence amongst each other that the effective sample size was barely adequate to be estimating anything with precision. So you had so much dependence, such a big sum here, you're dividing 1 million by a big number and you get a small number. All right. So these first generation MCMC algorithms tend to have rho sub n close to 1 and only slowly diminishing towards 0 as n, the gap between realizations, gets big. What I would call second generation MCMC algorithms, specifically in Stan, whose first version was released in 2011, which again probably sounds like a long time ago to you, but it wasn't a long time ago. I was here when it happened. Tend to have a first order autocorrelation that is negative. And subsequent autocorrelations could be negative, could be positive, but pretty close to 0. And thus, when we do this infinite sum, one of which is negative and most of which are close to 0, it could be that the denominator is less than 1. If the first one is sufficiently negative and the subsequent ones, even if they're positive, are sufficiently close to 0. This happens a lot. And consequently, if things go well with Stan, you can get an effective sample size greater than the nominal sample size, or similar to the nominal sample size. Or maybe if things don't go so great, half the nominal sample size. but not in anywhere close to the territory of the first generation MCMC algorithms, which would have autocorrelation separated by in periods close to 1. That does not happen with Stan. And like I said, the first one tends to be a bit negative, which is unheard of for the first generation. And that fundamentally is what makes the second generation algorithms better than the first ones. And so you should use them. Doesn't mean that the first generation algorithms were bad for their time. They weren't. But technology progresses, things get better. Should use the new stuff.
Sorry, could I ask?
Yes.
You mentioned it's possible for the effective sample size to even exceed the nominal sample size, but intuitively and conceptually, what would that mean then?
It means that this sum is negative.
Right, but how do we think about it in practice? Like if we know that our sample size is only this fixed number, then
Like
What?
1,000, yeah.
what would a larger effective sample size, how would we understand that, like intuitively or conceptually?
Well, I don't know how intuitive you find it, but it let's say your effective sample size is 2,000 and or let's say 1,500 and your nominal sample size is 1,000. Conceptually, it means the 1,000 dependent draws that Stan produces give you the same precision to estimate a posterior mean as 1,500 independent draws would. But conversely, with the first generation thing, if you do nominal of 1,000 and you get this severely autocorrelated thing, then you'd be lucky if you had one effective sample. In which case, it's kind of like you're estimating a mean with one draw. And that could be very imprecise, even if it's like in expectation, right? And so if I flip p to be negative 0.5, you can see that this is going up and down. Well, I should probably flip back and forth. But this is with the positive p, and you can see it's kind of jaggedy more. With the negative p, it's oscillating between positive and negative consecutive values more regularly. And so if I took any one of these, which they do have 1,000 dependent draws, but this might be worth 1,200, 1,300 effective due to the negative odd autocorrelation. And that's more or less what Stan achieves. So what is the MCMC algorithm that is the default in Stan? Like I said, originated with a postdoc named Matt Hoffman and was substantially modified in the intervening years by another postdoc named Mike Benincourt, both at Columbia for a while. It's more complicated than an AR1. It's not linear, lots of complications going on. But it is a discrete time Markov process. And so the previous continues to apply, but without the same simplifications that we get from linear AR1. So the first thing we do is we take the natural logarithm of base rule. So the logarithm of the posterior PDF of the parameters theta given the data and whatever went into the priors, that's the ... means whatever went into the priors, is because the logarithm makes a product into a sum, the logarithm of the prior PDF for theta given whatever, plus the logarithm of the PDF or PMF for the data given the parameters, minus the thing that comes from the denominator, so the logarithm of the marginalized PDF or PMF for y, irrespective of theta, but given the priors. So theta is a vector of k parameters, does not have to be a single parameter. And then we're going to introduce phi, which is a vector of k parameters, so k, same k. And these phis can be conceptualized in a physics sense as momenta, which is the plural of momentum in Latin and in physics, which you might not know But these phi parameters are going to have a prior, independent normals, expectation 0, standard deviation S sub k, and we'll get to what S sub k is in a minute. So like I said, this involves a metaphor of physics, and it goes well beyond what a typical QMSS student would know about physics, which is nothing. But it does not go that much beyond what a physics major would know about physics. So I think someone at MIT, Caltech, whatever, one of these people, if they graduate with a degree from undergraduate in physics, they would probably be able to do this. You know, it's not like we're going to have a physics question on the final exam, but you need to know a little bit about how STAN works, because we'll use STAN on the final exam. So the way I tend to think about it when explaining about it is think about Angry Birds. Okay? Angry Birds is a physics simulation. Do you think the people who created Angry Birds had to get like a Nobel Prize winner in physics to program Angry Birds? No. They probably got someone who's like 12 and said, here are the formulas, like make it into a video game. All right. So we're talking about like Angry Birds level physics here, not, you know, can we go to the moon? But actually, even going to the moon is not that difficult if you don't really care too much whether you land or whether you land upside down like the India people did last month or whatever. So if you're not too worried about that, then like landing somewhere on the moon is not that difficult either. All right? Getting back is a little tricky because you might burn up, but we're not going to worry about that either. Define energy as the sum of potential and kinetic energy. So the potential energy is thought of as this part, which comes from the logarithm of Bayes' rule for theta. And kinetic energy comes from this part, which is the logarithm of the K normal prior PDFs on the phi parameters. This all gets multiplied by -1 because you people's conception of gravity entails stuff being pulled down, but multiplying by -1 doesn't fundamentally alter anything. So the sum of potential, which is like the logarithm of Bayes' rule for theta, and kinetic energy, which is the normal prior on phi in logarithm terms, sum to h, Hamiltonian energy. And Hamiltonian, this is named after some guy, Hamilton, who figured all this out in the 1800s without the benefit of any calculators or computers or anything like that. So it is slightly more complicated and rigorous and correct than Newtonian physics, which was invented by Isaac Newton in the 1600s after the apple fell on his head, and so he invented physics to explain why. He didn't quite get it right. Hamilton had to make the whole thing a bit more rigorous in the 1800s, but still we're talking about something that has been extraordinarily well established for a very long time. Not quite as old as Bayes' rule, but close. Okay, so we got H, energy, sum of potential and kinetic energy, with this metaphor that the phis are somehow going to be related to momenta. And phi, as you saw in the previous, none of them enter the log likelihood. Consequently, their posterior distribution conditional on the data is the same as their prior distribution, which I said was normal, expectation 0, standard deviation S sub k. So whatever S sub k is, the posterior distribution of the phis is the same as the prior distribution of the phis. I can just draw, or to draw from the prior is the same as to draw from their posterior. You just draw from a normal. No big deal. Now the algorithm, or Matt Huffman's original algorithm, starts something like this. We're going to choose some starting values for theta. In principle, doesn't matter what those are, as the number of iterations goes to infinity. In practice, might make a little bit of a difference. But if you've chosen good priors, you can choose starting values by drawing from your prior once. And that's usually going to be fine. There's other things that are usually fine as well. And then for subsequent iterations, indexed by little r, all the way up to capital R, we're going to draw each of the phi parameters from their normal distribution, and then recalculate the Hamiltonian at iteration r. So this is now indexing. So we've updated the phis to iteration r. We still have the thetas that are left over from the previous iteration. And then we're going to introduce the concept of time. So Hamiltonian dynamics is a nonlinear continuous time Markov process. So it's going to evolve the thetas and the phis over time in a way that's consistent with Hamiltonian physics. And the main thing you need to know that Hamiltonian physics entails is that h at iteration r, so r is discrete, but h over continuous time remains the same. So in physics terminology, h is conserved. If potential energy goes up, kinetic energy has to go down by the same amount, such that their net change is 0 over time. That's the kind of defining characteristic, one of the defining characteristics about Hamiltonian physics. Total energy is conserved, even though potential energy and kinetic energy go up and down in a zero-sum fashion. Another way to phrase this is there's no friction. The only force is due to the phis. So you can think of the momenta implied by the phis is like an instantaneous gust of wind that lasts for no time, but it pushes the thetas around, and then the thetas proceed over time with no friction, because friction would reduce the total energy, or it would change some of the energy into heat. We're not doing that in our simulations. We don't do that in Angry Birds. Even though the bomb bird like blows up, it doesn't create any heat when it does that. All right. So Hamiltonian dynamics is going to go over time, and because the value of h at iteration r stays the same over continuous time, that is a crucial fact because it allows us to drop constants such as the logarithm of the PDF or PMF of the data irrespective of theta, which we don't know anyway. So we don't know their value, but we do know that their value is conserved under Hamiltonian dynamics. And that's enough, actually, to allow us to proceed to part 3. So in order for this to proceed, we need to solve a so-called initial value problem that are governed by Hamilton's system of ordinary differential equations, where the total derivative of theta over time is equal to the partial derivative of the Hamiltonian with respect to the momentum parameters, and the total derivative of the momentum parameters with respect to time is equal to the negative of the partial derivative of the Hamilton with respect to theta. And the partial derivative of the Hamiltonian with respect to the momentum, no big deal. Just differentiate this with respect to phi. The 2's cancel, you're left with phi over s squared. So that's, we could do that. And the partial derivative of the Hamiltonian with respect to all of the parameters theta, aka the gradient, depends on what your model is. And that would be tedious at best for humans to calculate. But there's really no reason why a human should be calculating a derivative in 2023 nor in 2011. That is something that is fairly easy for computers. And moreover, it does not involve the partial derivative of the logarithm of the denominator of base rule with respect to theta, because although we don't know what this is, we do know that it does not involve theta after we've integrated theta out. Consequently, the gradient of that term with respect to theta is 0. And basically speaking in terms of physics, if I know the derivative of stuff, that is sufficient for telling me how stuff is going to move. So by taking the derivative with respect to time implicitly, I more or less figured out what's the velocity of movement in the parameter space of my Markov process. And if I know how stuff moves, that's adequate, sufficient. All right? And I know how it moves because I know the derivative totally exactly, because the only thing that I don't know is a constant. And I do know that the derivative of a constant with respect to a variable is 0. So I totally know what the derivatives are. And the derivatives give me velocity, and velocity gives me movement. And I just need to keep track of where things go if they have, this or that realization of velocity. If everything was standard normal, we could solve this analytically. In general, stuff isn't standard normal, so we have to do this numerically. But there are good algorithms, numerical algorithms, for solving this particular initial value problem. And so this process is going to produce realizations of both theta and phi. We don't really care about phi, so that gets ignored. But we get realizations of theta, whose PDF is proportional to e raised to the power of the negative Hamiltonian. So that negates the previous negation that I did because of the gravity thing, and undoes the logarithm. So it's give me stuff that's correct or proportional to the true PDF of the parameters given the data. Which brings me to part 4. Hamiltonian theory presumes that time is continuous. With MCMC, we're going to discretize time in order to solve that initial value problem using the so-called leapfrog method. Works well, introduces a small amount of error each time we solve that initial value problem. But if the step size of the leaps is sufficiently small, then the error at one step tends to wash out with the error in any other step. And so you basically, over multiple steps, get an error that's pretty close to 0. Close enough. But if the step size is too big, then the error in one step tends to accumulate with the error in another step, which can lead to a so-called divergent transition, which you probably won't encounter until after spring break, but just be aware that that really meant your error was too big, and so it tended to accumulate rather than cancel, and your physics thing went off to the moon instead of staying, where it was. Which theoretically can't happen, but on a computer it could, and you get a warning about it. So I said, well, how do we choose S? Well, Stan has some heuristics for doing this for you, such that the error in any one step is going to be sufficiently small, tending to cancel rather than accumulate. So you don't even really need to choose S yourself. It's done for you in order to avoid this thing where the errors accumulate. So part 5, total integration time. It's a random variable. The number of steps that you take. And the integration is stopped rather artificially, but in a reasonable way, when the trajectories going in positive time and negative time start to get close to each other again. This is what's known as a U-turn. And the specific algorithm that Matt Hoffman came up with, he called the no U-turn sampler. Because when the thing started to make a U-turn, it would just stop it on that iteration rather than going back to where it came from. And when the iterations hit the U-turn point, Stan will choose a realization of the parameters with probability density proportional to the footprints of where it has been previously on that iteration. As the proposal for that iteration, there's an acceptance or reject thing, applies the Metropolis criterion, which you saw in the reading. But unlike the first generation algorithms, which, like I said, would reject a whole lot of proposals, With Stan, like 80% or more of proposals are accepted, which helps reduce the positive dependence. You can think about this. If you have a proposal that gets rejected, then it's exactly the same as the previous realization. And so you get strong positive association with consecutive realizations if you have a high rejection rate. But with Stan, the rejection rate is low, and consequently the dependence with the previous is not so big. So across all 5 parts of this and other parts which I haven't really explained, and subsequent modifications which I also haven't explained, and future modifications that people are doing even today to try to build a variation of Stan that's even better. But almost everything that's been done the past 10 years has been using physics metaphors and gradients and movement and stuff like that. But to make a long story short, users pretty much just need to specify the logarithm of base rule, logarithm of the prior PDF, logarithm of the data PDF or PMF given theta, and then the MCMC algorithm based on physics in Stan can mostly handle the rest, including choosing of the optimal S, the standard deviation of the momentum. And we can see this in a video, which was not made by me, because I don't know how, but this is illustration of the original version of the Stan algorithm. So we have, no, go away. 3 parameters here, like alpha, beta, and sigma. And what you see as this goes along, so it's a little bit small. I'm already full screen. These dots that you see are the progression of the Hamiltonian thing in positive time and negative time. And so as, can I go slow? Okay, slow is good. As it proceeds, so this is going in like positive time, this is going in negative time. Once the ends of these start to get closer together, then it's going to stop it for that iteration and choose one of these dots as the realization with probability proportional to posterior density. So it looks like it's starting to turn around now. It's still getting a little bit farther apart. Okay, back up. Okay. So it was almost at the U-turn point here, where this endpoint started to get closer to this endpoint, and then it randomly chose one on the footprints that it's been, which comes out as like a big green dot right here. It gets randomly chosen. Right there, okay? Then it goes on the next one again, it's looping around. But anyway, it's transversing through a 3-dimensional space, and it manages to go pretty far before it gets to the U-turn point. And so it kind of gets all the way across the parameter space, and thus gives you really good draws with low dependence in general, and the dependence between consecutive values tends to be negative as a consequence of the fact that it goes as far as it can in both directions before it stops. And because it's going as far as it can, you tend to get negative association with the previous realization. Okay, enough video. It'll be on the GitHub. So Stan includes its own language. It's a simple computer language, but even though it's simple, we're not going to learn it this semester. I said you needed to have a passing familiarity with R, and we're going to stick with that. But there is an underlying Stan language. What we're going to do starting next week and after spring break, the Stan programs will be given to you, so you don't have to write them in the Stan language, but nevertheless, writing them in the Stan language is not difficult if you needed to do that later on. So here's an example of a Stan program that would draw from the posterior distribution that Pfizer should have used, not the one that it did. First, we have a variety of things which are considered data or constants, everything to the right of the vertical bar and Bayes rule. such as M, the expectation of a normal prior on vaccine effectiveness, that is going to be forced to have an upper bound of 1. S, the standard deviation of the normal prior on vaccine effectiveness, that's going to have a lower bound of 0. Then we have N, it's an integer number of people in the randomized controlled trial with COVID, and Y, an integer between 0 and N inclusive, the number of those people who were vaccinated. Okay, so everything to the right of Bayes' rule is claimed to be data. Then we have parameters. In this case, there's only one. The vaccine effectiveness with Stan language easily allows there to be multiple, even millions. I've seen parameters. So this is everything to the left of the vertical bar in Bayes' rule. So vaccine effectiveness also has an upper bound of 1 because it's 1 minus the ratio of the probability that you get COVID given that you're vaccinated divided by the probability you get COVID given that you got the placebo in the randomized controlled trial. So that in this case is our only parameter. Transform parameters block allows any mapping from the parameters that we're interested in keeping. So maybe theta is something we might be interested in keeping. It's a real number between 0 and 1 continuous applied by inverting the formula that takes from theta to vaccine effectiveness. Just do the inverse. Now we get theta. And in the model block, this thing called target pretty much initialized to 0. And then we're going to increment it with the logarithm of our normal prior PDF for the vaccine effectiveness given expectation M and standard deviation S. And we're also going to increment it with the logarithm of the likelihood under binomial. So the logarithm of the probability of Y people getting COVID who are vaccinated out of N people total getting COVID, given the success probability implied by the vaccine effectiveness. Increment with the logarithm of prior PDF, increment with the log likelihood. And the model block is essentially a function that returns target, which is the potential energy here. You don't even have to mess with the fees. That happens in the background automatically. And you don't even see the fees. So that's the whole thing, 17 lines. Pfizer could have done this, would have been much better than what they would have done, but it would not have made a difference as to the conclusion that their vaccine is extraordinarily effective. You run this, after it compiles, it takes like a second, probably less. To do, you get a whole bunch of draws that are summarized here. So we would get a posterior mean, a posterior median vaccine effectiveness in the mid-80s rather than the low 90s that the press release that Pfizer put out claimed. But we would be quite sure that the vaccine effectiveness is more than 70% effective, even more sure that it's greater than 50% effectiveness. So plenty sure that the FDA should approve this, but with what I would argue more realistic prior. And this thing is our object, has a whole bunch of stuff in it, but if you want to and need to, you can coerce it into a data frame. It's going to have 4,000 draws on each of the three things. So LP is the alias for target. You ordinarily wouldn't really worry about it. But you get realizations of vaccine effectiveness. You get realizations of theta. You get 4,000 of them. But you just need to remember that the rows are not independent of each other. And that's something to keep in mind. So this came from a Markov process. But consecutive rows tend to have negative association because the algorithm in Stan is much better than those first generation algorithms. Okay, out of time for today. I'll post the second homework tonight. It'll be due before class next week. And then next week we'll start learning about linear models with Bayesian estimator, MCMC, Stan, all that. Okay, and so if you have any questions about the homework, be sure to ask about them on Ed Discussion using the option for private thread.